Hey guys, this is Aaron Carmen from AXC Electronic, back with the next video in our circuit analysis lecture series. So last time we talked about low pass and high pass filters, and today what we're going to be doing is we're going to be looking at a new filter type, and then we're also going to be looking at, what happens if we need some sharper cutoff or some more attenuation in these filters. Okay, so first thing we're going to do is I'm just going to go ahead and get out of your way, and we can get started right away. First thing we're going to do is that I want to just review I want to review the filters that we've talked about. So first filter I'm going to say is LPF. And you should be able to see what that stands for. That stands for low pass filter. Okay? Now, low pass filter is going to allow low frequencies to pass through, and it's going to attenuate high frequencies. Okay? So we're expecting the frequency response of a low pass filter, okay, on a logarithmic scale. So I'll do AV dB. We're expecting it to look something like this. So it's going to let those lows pass, and then it's going to start dropping like that at the cutoff frequency. Now this is ideal. It's not going to look exactly like that, but it's kind of a good approximation. So if you're having to draw these by hand, this is a kind of a good approximation. Okay? Now the next kind is the high pass filter, or I'm going to call it HPF. Okay? So the high pass filter, again, is only going to let high frequencies pass, and below its cutoff frequency, it's going to attenuate. So we graphed its frequency response. I'll go ahead and draw FC here. Above that, we're going to expect it to be pretty flat, and then below that, it's going to attenuate. Let me just make sure I'm clear that this is AV dB. And again, this isn't going to look exactly like that. It's going to be sort of a smooth curve, not just a sharp transition, but it's a good enough approximation. Okay? So these are the two sort of simpler circuits. And we looked at the RC circuits and how we can derive the expression for output voltage versus input voltage. Okay, but what if we need something a little bit more complex? Okay, so what if we need something, for example, what if we need a frequency response like this? So what if we need, we are only interested in a certain band. So we want a lower cutoff frequency, so I'll call that FCL, and then we want a higher cutoff frequency, FCH. So we're saying we're interested in this little area between FCL and FCH. We're only interested in this signal. Everything else we want to get rid of. Well, is this possible? Can we do this? Is this something that has been done before? And the answer is yes, it has been done before. It's it's pretty not too hard to do. So if you look at this, let's look at all three of these images kind of in one view. That way we can sort of make some connections. You'll see that for this half of the graph, if we look on the left half of the graph, this is going to look kind of like a high-pass filter. So this is just a high-pass filter. Now over on the right side of the graph, what we're going to see is that we, again, have a filter, except this one is sort of a low-pass filter, right? So we're going to have a low-pass filter and a high-pass filter. If we combine those two, then we can create what's called a band-pass filter. Okay, so I'm going to call this band-pass filter. Okay, because we're only passing a certain band or a certain frequency band. A frequency band is just a group of frequencies. So I could say between FCL and FCH, that is the band I am interested in. So bandpass filter. I may also abbreviate this BPF for band pass filter. Okay, so let's say that we want to have a bottom cutoff frequency. So I'm going to say we have FCL is equal to 100 hertz. Okay, so we're going to have a lower frequency of 100 hertz. And now our higher frequency, FCH, is going to be 10 kilohertz, or 10,000 hertz. Okay? So let's say that is our band of interest. That is what we're interested in keeping. Everything else we want to get rid of. Okay, well, the first thing that we need to do is we're going to start off with a high-pass filter design using, again, this lower frequency. All right? I know it's a little bit counterintuitive to use FCL, the lower cutoff frequency, for a high-pass filter, but that's because you need the high-pass filter to let through stuff starting at the lower cutoff frequency. So we can use the formulas that we already know. I'm going to use the RC formulas that we talked about before, so RC high-pass filter. And just to sort of take some of the, take sort of the ambiguity out of it, I'm going to say we know for a fact that our R is going to be 1 kilo ohm. Okay, so I know FCL is going to be equal to 1 divided by 2 pi RC. Okay, 2 pi RC. We know FCL. We know 2 pi, clearly. We know R, because we were given R. So all we have to do is calculate for C. Okay. Now, if you're not given R, you can choose any R that you want and then choose any C that you want. Or, you could do it vice versa. You could choose C and then decide on your R based on what you have available. But for us, I'm just going to go ahead and start with this 1 kilo ohm. So what we can do is that we can just rearrange this equation, really simple algebra, and we'll get that C is equal to 1 over 2 pi R FCL. Okay. And then we can plug this in to get 1.6 microfarads. Okay, 1.6 microfarads. And this is for our high-pass filter. Okay. Now, let's do the next one. So the next one is going to be our low-pass filter. We're going to again say that our R is limited to 1 kilo ohm. Now, for this one, we'll say FCH is equal to 1 over 2 pi RC. So all we got to do is, again, we know R, 2 pi, and FCH. Just rearrange and solve for C. So what we'll end up getting is that C for the high-pass filter is equal to 16 nanofarads. Oh, sorry, not for the high-pass filter. For the low-pass filter. So this up here, let me make sure. Yeah, so this up here was for the high-pass filter, and this one is for the low-pass filter. Just wanted to make sure that I was clear on that. Okay, so now we have, let's look at our high-pass filter. The high-pass filter that we came up with is capacitor and a resistor. Okay. So our resistor is 1 kilo ohm. Capacitor, we said for the high-pass filter, is 1.6 microfarads. Now, for our low-pass filter, what we'll get is that we have resistor and capacitor. Now, this resistor is, again, 1 kilo ohm. The capacitor is 16 nanofarads. Pretty sure, yeah. So, we've got our two individual filters. Now, how should we connect these up? Okay, well, we're expecting that if something can pass through this first one and pass through the second one, that we want to make it all the way through, right? If it is in the pass band of both of these filters, then it's going to make it through the entire bandpass filter. Okay? And really, that's just my way of saying that we connect them together just like this. Okay, so our final bandpass filter is going to be this 1.6 microfarad capacitor, a 1 kilo ohm resistor, another 1 kilo ohm resistor here, and a 16 nanofarad capacitor. Okay, so this is our V in and our V out. Okay, so this is how we're going to create this bandpass filter. So if we were to plot the response of this bandpass filter, which I did this in LT Spice just to make sure I was doing everything correctly. If we plot the response of this filter, this one ends up working out pretty good. Okay, so we have our two cutoff frequencies. Let me call this, I'm going to go ahead and make sure that I say this one is 100 hertz and that this is 10 kilohertz. Oh, almost did ohms there. 10 kilohertz. Between those two, we're going to have a pretty flat response, and then on both sides of it, at minus 20 dB per decade. So if we're not in that pass band, we're going to be attenuated based on the frequency we have and this slope. Okay. So if we're, let's say we're at 100 kilohertz and we want to know how much attenuation we're going to have. Well, that's 1 decade away from 10 kilohertz, so that means we're going to have minus 20 dBs of attenuation there. Okay, so the thing to remember about this is that this isn't the real plot, okay, because the real plot is going to have these non-idealities. It's going to have sort of a curve here, it's going to take a little bit of time, then a curve here. It's going to be a curved line. It's not just going to be straight, it's not just going to be a straight pass band, okay? Now, for this filter, it doesn't really matter too much because we picked our two cutoff frequencies pretty far apart. Okay, so the minus 3 dB point for the high pass filter is pretty far away from the minus 3 dB point for the low pass filter, so they don't really have too much interaction, right? But what happens if we move these cutoff frequencies a little bit closer together? Okay. So this is something that I sort of experimented with because I wanted to make sure that I was giving you accurate information. So what you find is that if you move these cutoff frequencies closer together, so say instead of 100 hertz and 10 kilohertz, I have 1 kilohertz and 10 kilohertz. Okay, I'm going to plot the red or the ideal in red. So we're expecting the ideal plot to look something like this, right? So that flat passband and at minus 20 dB per decade. Okay, let me make sure I put all the information on here that we need. So minus 20 dB per decade. But what you find is that whenever you actually simulate this circuit, what you'll have is that you get something more or less like this. Okay, so you have a very curvy looking line, right? You have that very curvy looking line. It doesn't even quite hit 0 dB. So look at here. We're expecting in our passband that we're going to have 0 dB. Okay? And whenever, whenever those two cutoff frequencies are far enough away, up here we got to a point where even our realistic response is pretty close to 0 dB. But what happens is that whenever those two cutoff frequencies get closer and closer together, you're going to start having more and more interaction between the two, okay? Because originally we just said, well, let's just connect them, two filters in series, bada bing, bada boom, and then we end up with this idealized response. But what happens is that if you move those two cutoff frequencies too close together, that you're going to start having more complex interactions, and we're not going to be able to sort of think of it in a simplified manner. Okay, so this is something that you kind of have to be aware of. So if you start moving those cutoff frequencies too closer together, and just based on what I simulated today, I would say if they are within 2 decades, for this first one here, we had 2 decades between the two. For this one, we only had a single decade, and this is where it started looking a little bit worse. So I would say 2 decades is enough to where you can sort of think about an ideal response, and then closer than that, you're going to start having these other effects that come into play, so you're going to have to start simulating those. Okay, so like I said, just whenever you have those two cutoff frequencies so close together, it's harder to characterize what V out over V in is going to be. So just simulate the circuit to save yourself a little bit of headache. You can adjust things however you need them. Okay, so this is pretty much all I wanted to say about bandpass filters, because they're either pretty simple or they're pretty complex. On the simple side, you can say that it's just 2 filters in series, but on the complex side, we would have to do a ton of math just to get the output versus input. Okay, so that's something that I'm not going to do because I think that would only confuse us. It would confuse me for sure. So that's something that we're not going to do, and I'm just going to tell you, if it's closer than 2 decades, simulate it. So the next topic for today is higher order filters. So I'm going to go ahead and just draw a line here. We're going to start talking about higher order filters. So far all the filters that we've seen have had a minus 20 dB per decade roll-off, right? Well, what if we need something steeper than that? What if we have a frequency that's 1 decade away that we need attenuated by, let's say, 40 dB? Well, how can we really get that? We can either move our cutoff frequency over a little bit more, but if we do that, then we might be attenuating stuff we don't want to attenuate. So the answer to this is let's, just add another filter in series. Okay, so think about it like this. This is definitely an ideal discussion, but if we have a low pass filter, okay, if we have a low pass filter and we put it in series with another low pass filter, we're expecting that once the signal has passed through both of those, it's going to have double the response. Okay, so it's going to be, let's say, halved and then halved again, so it'll be left with 1/4. Okay, and this is sort of kind of what happens. So if we need the sharper roll-off, the answer is we're going to use what's called a higher order filter, okay, or just adding another filter. So I wanted to define the filter order. So we're going to use N for the filter order. So I'm just going to say the filter order N is just the number of reactive components. That is the simplest way to put it. I'm sure that there's a more technically correct way, but I think this is the simplest way to put it. So if we have 2 capacitors, that means it's going to be a second order filter. And this is sort of a question I had. If we have this bandpass filter, we have 2 capacitors in here. Is this a second order filter? And the answer is yes. Here, N is equal to 2. This is a second order filter. Okay? So let's go back to our low pass filter discussion. Okay? So these higher order filters, like we said here, if you imagine these 2 low pass filters in series, that is going to provide more attenuation for us. Okay, because if something is getting filtered in the first, it's going to get filtered in the second, so that its attenuation is going to double. So let's say that we needed a high pass filter, or let's sort of generalize something first. So the roll off is normally, minus 20 dB per decade. So minus 20 dB per decade normally. Or that's for n is equal to 1. Okay, so if we have a first order filter, that means its roll off is going to be minus 20 dB per decade. Now, the roll off, actually, we can define it as more like this. This is definitely, again, just more of a generalization, but I think this sort of helps drive the point home. Okay, so the roll off for this filter is going to be its order times 20 dB per decade. So that means if we need a high pass filter, so let's say, for an example, we need a high pass filter with minus 40 dB per decade roll off. So like I said, there's a signal 1 decade away that we need attenuated by minus 40 dB. How can we handle this? Well, we know how to design a high-pass filter with a certain cutoff frequency. Okay? So all we have to do is sort of increase its order. Okay? So we can use 2 filters with the same cutoff to make a second-order filter. So if we were to design this high-pass filter, let's say high-pass filter, looks something like this. Right, just an RC high-pass filter we're measuring across that resistor. Let's say we're using a 1 kilo ohm resistor again, just to keep sort of some good consistency. What we can find is that C is equal to 800 nanofarads. And this is, just for an example, I pulled, let's say that we want to cut off of 200, let's say we want to cut off of 200 hertz. So our cutoff frequency is going to be 200 hertz. And above that, we want it to pass. Below that, we want it to be attenuated. Well, this is a first-order filter, right? Because we only have one reactive component, that capacitor. This is a first-order filter. This isn't going to provide the roll-off we need. If we want to provide that roll-off that we need, what we're going to need is we're going to need another filter in series. So I'm just going to go ahead and draw that for you. If I just put this other filter in series, you can see that now we have 2 capacitors, so we have a second order filter. You can see it's just a copy of itself in series, 800 nanofarads and 800 nanofarads. Nothing has changed, we just added another filter. Okay? Now, again, this is very sort of an ideal, imprecise design. There are ways to do this more precisely. There's sort of tables that you can use for specific types of filters, specific types of responses, but just for sort of an intuitive discussion, this is what I wanted to show you. You can add a filter to a filter. That'll make it a second order filter and sort of increase that roll off. So a note that I want to make is that normally at our FC, this is going to correspond to an attenuation of minus 3 dB, or a 1/2 power reduction. But let's look at this case up here. So if this FC is 200 hertz, this FC is 200 hertz. Well, we're going to get half power here and half power here. So that means we're going to have a quarter of the power on the output. And this corresponds to minus 6 dB. So for this n equals 2 filter, or a second order filter, the 3 dB point is now a minus 6 dB point. So like I said, our stuff is sort of changing a little bit. So for these higher order filters, this is something that, again, that you'd want to simulate to confirm. And I guess that's sort of the theme of this video, is that for stuff beyond simple low pass or high pass filters, you really do want to sort of simulate it just to make sure that you're doing things correctly. Ideally, you'd want to simulate every filter, but for these second order filters or for bandpass filters, you're going to want to simulate these circuits to make sure it's behaving the way you thought, okay? Because it might not always be as simple. Okay? So let's just see what this response is going to look like. Okay, so I'm going to plot the ideal response first. So for this high pass filter with an FC of 200 hertz, ideally, we're going to have a flat response above that and then an attenuation below that. Okay, so this is n equals 1. And I'll make 2 graphs. So I'm going to call this one the ideal. And then I'll make another one for the realistic case. So for n equals 1, we're expecting to have just that sharp elbow at FC. And then for n equals 2, we're expecting to have that same high pass, or that same passband response, and then a change in that roll-off. So for n equals 1, this is minus 20 dB per decade. For n equals 2, this is minus 40 dB per decade. Okay. Let me make sure I note it here. N equals 2. So for that second order filter, we're getting that sharper attenuation, okay, or that steeper roll-off, okay? And you can even generalize this, to like a third order filter if you wanted to, and you could have something like this, or super sharp roll-off, okay? And this would be minus 60 dB per decade. So you get what I'm saying? Adding that order, or adding that other filter in series is going to improve the roll-off. But now, like I said, this is the ideal case. Let's look at the real case, okay, just to get a sense of what's going to happen. So this is the real case. Let's say FC is right here. So for the real case, let me note here that this is n equals 3. For the real case, what's actually going to happen is that we're going to have a little bit of a roll-off here. Because in the real case, remember, we have minus 3 dB at this point. And this is for n equals 1. And this is a minus 20 dB per decade slope. Now for n equals 2, we're going to have a similar higher frequency response, but it's going to curve sooner and have that steeper slope. So here it's minus 6 dB, and this is minus 40 dB per decade. And you can keep this pattern going for n equals 3, in having that same passband response, or that same high frequency response, and then once we get close to the cutoff frequency, a steeper cutoff here. So this could be minus 60 dB per decade, and this would be minus 9 dB here, because you have another half power, reduction, so that would be another minus 3 dB. So this is something that you have to consider, that your minus 3 dB point is going to change for these second order filters if you do it this way. That's why I've tried to really drive home that for these higher order, more complicated filters, what you're going to want to do is simulate them, because it's harder to do on paper and figure out on paper what that frequency response is going to look like. Okay? So that's the message of today, is that these bandpass filters, it's good to have an intuition of how they work. It's good to have an intuition of it's just 2 filters in series. Same thing for these higher order filters, but really in practice you're going to want to simulate them before you implement anything. Okay, so if you guys have any questions, please feel free to leave them in the comment section below. I really enjoy answering those questions that you have, because I want to see you guys master this material. If you like this content, please give me a thumbs up, subscribe, and you can ring the bell to get notified whenever my next video comes out. In this next video, we're going to be talking about resonant circuits. And this next video is actually going to be the last video for our circuit analysis lecture series, because beyond this, I think that if I were to have any more lectures, it would get into stuff that's too complicated, too specialized, and I don't want this to be just a super hard math channel. I want this to be something where you can get an intuitive understanding and then maybe do a little bit of practical math here and there, but I don't want to make this just super hardcore heavy math. So in this next video, like I said, we're going to be talking about resonant circuits. This is a really good fundamental concept to know before you continue on looking at maybe any other field. Okay, so resonance is something that's important to know. But like I said, if you guys like this content, please give me a thumbs up. I really do appreciate it. And I'm Aaron Carmen, and thank you for watching.